Hey guys, I've gotten a lot of questions about how to set up the block on the ramp problem. So I figured it was probably most efficient just to record a video and walk you through it. If you have any questions, feel free to post on the discussion forum or send me an email and I can clarify anything. This is my very first video. I usually explain things in person, so I don't have faces to gauge how well I'm presenting something or whether it's being understood. So I apologize in advance if things get a little bit either too technical or moving too slowly. Feel free to give me as much feedback as possible if you have any suggestions. Okay, let's jump into it. I've got a block on a ramp, and you guys have seen this problem on the quiz and in the practice problems. You're given either the angle and you're asked to find the acceleration or maybe the normal force, or vice versa, you're given maybe the acceleration and you're asked to find the angle. Either way, no matter what you're asking for, the setup is going to be more or less the same. And really the big question is, how does our angle theta relate to the forces that are acting on the block? So the first question we want to ask ourselves are, what forces are acting on the block? Well, the safest one is always going to be force of gravity. Force of gravity is always going to be pulling vertically downward, and it's the reason that we're not all floating out into space. So, force of gravity, vertically downward. Now, it does act from the center of our block, but I can pretend that the block is kind of just like a point mass, and I'm gonna, for geometrical purposes, bring this guy to slide down just a little bit. There we go. Okay, so we have our force due to gravity pointing vertically downward. But the block is obviously not just falling through the ramp, so we need to add another force. That force is going to be the contact force between the block and the ramp. The contact force, it's tempting to want to say it's going to be acting vertically upward to oppose gravity, but normal forces don't work that way. Normal forces are going to be acting in the direction perpendicular to the way that the two objects are touching. So the two objects you can kind of think of as coming to contact in this way. So the normal force is going to be directly perpendicular to that. So directly perpendicular to the surface of contact between the ramp and the block. Okay, so those are the only two forces acting on our block. And the next thing we want to do is define a coordinate system. Usually, we take our coordinate system to say that the vertically up position is going to be positive y, and to the right is positive x. But for a tilted system like this, that's actually not the most beneficial way. Instead, what we'd like to do is tilt our coordinate system so that the y direction is is lined up with the normal force, and so the x direction, actually, instead of being lined up the ramp, I'm going to line up positive going down the ramp. Cool. So now our Cartesian coordinate system, instead of being up and to the right, is going to be off the face of the ramp and down the ramp. This is going to become beneficial when we move into our next step, which is breaking up the forces into the x and the y components. You might ask, well, why do we need to break them up into the x and y components? It's because forces are vectors, and often when dealing with forces, we're going to use Newton's second law. Newton's second law says that the sum of the forces is equal to the mass times the acceleration of the object. But forces and acceleration are vectors. And so I can't just write this, normal force plus gravitational force is equal to mass times acceleration without breaking it up into the x and the y components. So what I can do is I can say that the sum of the forces in the x direction is the mass times the acceleration in the x direction, and the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. Immediately, I can recognize that the acceleration in the y direction is going to be 0 because I've taken my x direction to be along the face of the ramp. The block is either going to slide up and down the face of the ramp. Now, ours is going to slide down the ramp because there's nothing pushing it back up. But if there was something that was pushing it back up, then the block would be sliding up the ramp. Either way, it's not going to be bouncing up and down here along the y direction. It's not going to be like bouncing down the ramp. It's not going to be flying off or falling into the ramp. So the acceleration in the y direction is 0. The acceleration in the x direction, though, we can't just assume it's 0, and in fact we'll find that it's not 0 because our block could be and winds up, it is, sliding down the ramp. Okay, so now we want to talk about what the normal force and the gravitational force are doing with respect to the x and the y direction. The way that we've defined our coordinate system, we can see that the positive y direction is lined up directly with the normal force. That means that the normal force has only a component in the y direction. It doesn't have any of its vector pointing in the x direction. So the sum of the forces in the y direction, we can begin by saying, well, that's going to be positive normal force. Positive because the arrowheads are lined up, so the normal force is pointing in the positive direction, the positive y direction. Great. Now we want to figure out how the gravitational force fits in. Well, let's go ahead and take a look at some of the geometry that's going on in our problem. We've got a right angle there. And so what we can say is, using the fact that all angles inside of a triangle, so all angles inside of a triangle should add up to 180 degrees. Well, we've got 90 of it there at the right angle, so the other two should add up to 90, because 90 plus 90 is 180. So that means that this angle theta and this angle, whatever it is, maybe call it alpha, theta plus alpha should add up to 90 degrees. That means that that top angle alpha is 90 degrees minus theta. So we can write it like this: 90 degrees minus theta, and that's this angle here. Okay. How does that help us? Well, what I can do is I can continue this y vector. Let's see, how do I want to say this? I can pretend like there's a vector here that is parallel to the normal force, but going in the opposite direction, so that we actually call that anti-parallel. So anti-parallel to the normal force. And what this vector is, this orange vector that I've just drawn, is the projection of the gravitational force onto the y-axis. Because the y-axis is going like this, so we can see that this is parallel to the y-axis. This is the projection, how much of this vector is lying on the y-axis. So that vector is actually the gravitational force y component. So the y component of the gravitational force, or in other words, how much of the gravitational force is in the y direction as we have defined it. Okay, so we want to do the same thing for the x coordinate. We want to figure out how much of our gravitational force is in the x direction. So what I can do, and I think maybe I'll do it up here first just to highlight, this is the projection. So I would draw, when I say projection, I mean like drawing the a vertical line or a straight line from the tip of the arrow to the y-axis and the x-axis, and that tells me how much of the vector is in the x direction or in the y direction. So I can see that FGX is up here, but it actually doesn't matter if I draw FGX up here or if I slide it down here. And I can see I drew this arrow a little bit too long, so we'll shorten that up a little bit. So FGY, FGX, I can slide it down here. The same way that I could slide the gravitational force earlier, I can also slide the gravitational force in the x direction. As long as the vector is pointing in the same direction, it doesn't matter whether I have it here or if I move it around, it's the same vector. So, as long as I preserve the length and the direction. So, I can write the gravitational force in the x direction. I can draw that vector down here. Awesome. You should be able to recognize here that I have a right triangle because the x and the y components are perpendicular. They have a 90-degree angle between them. So then the y components and the x components of any vector are also going to have a 90-degree angle between them. All right, how does that help us? That helps us because we can see that this is also a 90-degree angle. This is a 90-degree angle because we said our y component was perpendicular to the surface of the ramp. So then the negative y component is also going to be perpendicular to the surface of the ramp. If this is a 90-degree angle, that means that these two angles, 1 and 2, must add up to 90 degrees. And that means that this angle, we can call it something like beta. Beta and the angle next to it, the 90 minus theta, should be equal to 90 degrees because they make a right angle. Okay, we can subtract 90 on both sides and we can move theta over and we get that beta is equal to theta. Awesome. So now instead of writing that as beta, I'm going to write that as theta. And now I have how theta is related to the components, the x and the y components of the force. So let's slide this kind of out of the way for now. We used that. Okay, so what we can do is I'm going to draw this triangle here, and I'm going to slide it out over here, and then I'm going to rotate it. So actually, let's label it before we rotate it. This is the gravitational force. This was the gravitational force in the y direction. This was the gravitational force in the x direction. And this was theta we found. So now, I'll rotate that. Okay. And the next step we're going to do is we're going to use SOHCAHTOA. SOHCAHTOA. We're actually going to use SO and Ka. We're not really going to use TOA, but it is also still valid. So tells us that sine of theta, S, is equal to opposite, O, over hypotenuse, H. So you can see so. And then we also have that the cosine of theta, so CAH, is adjacent over hypotenuse. And tangent is opposite over adjacent, but we already have opposite and adjacent in the sine and the cosine equations, so I'm not going to worry about it here. Let's go ahead though and look at this triangle and figure out what are the adjacent, the opposite, and the hypotenuse sides. So if we look closely or carefully, or if we think about kind of the process that we've followed up to this point, the gravitational force, the full vector, is going to be the hypotenuse. So this is going to be the hypotenuse because that's the full vector. And then we broke it up into its x and the y components. So these are going to be the adjacent and opposite legs. And we define adjacent and opposite with theta. So adjacent means next to. So we want to figure out which side is next to theta. Well, FGY here is right there next to theta. So this is our adjacent side. And we can see that this is the side opposite of theta. With that, we can go ahead and rewrite sine of theta is opposite was FGX and hypotenuse was FG. And we can write that the cosine of theta is equal to FGY over FG. What I'm going to do here is multiply both sides of both equations by FG. We can see that it's going to cancel out on the right side. FG is on the numerator and the denominator, so we get canceling out there. And finally, we're left with the relationship that FGX is FG times the sine of the theta, and FGY is FG times the cosine of theta. Great. So now we have FGX and FGY defined by the angle and the gravitational force. Great. Now we're ready to plug these back in to our sum of the forces. So we'll plug the x component into the sum of the forces in the x direction. So far we had none because the normal force did not have a component in the x direction. So we have Fg times the cosine, the sine of theta. Notice that sometimes when we're talking about right triangles, we tend to think cosine is always corresponds to the x direction and sine always corresponds to the y direction. But notice that that's not always true. We found in the geometry of our problem that the opposite was true, that the x component corresponds with the sine of theta and the y component corresponds to the cosine of theta. Okay, If you have any questions about that, feel free to either email me or we can talk about it in person or post to the discussion forum. Okay, so then the only thing left is to add the y component to the sum of the forces in the y direction, but the y component is going to be negative. The x I took down the ramp to be positive, and the gravitational force in the x direction is moving down, acting down the ramp. But the y direction I took up and away from the surface of the ramp to be positive, but the y component of the gravitational force is acting into the ramp. So that means that when we add it in here, it's going to have a negative sign. So we have Fg times the cosine of theta. Excellent. So now we're ready to start solving for things. So I'm going to copy and paste these down here. I'm going to get rid of this one and keep this. Okay. So given these two equations, we can find everything that we need. From the top equation, I can plug in mg here instead of Fg. I'm going to write mg because the gravitational force is equal to mass times gravity. And I'm going to do the same thing here, mass times gravity. And the mass appears on both sides of the top equation, so I can cancel it out. So the first equation leaves me with the acceleration in the x direction is g times the sine of the angle of the ramp. And the bottom equation tells me that the normal force is equal to the mass times the gravity times the cosine of the angle of the ramp. Great. No matter what I was asked for, I can go ahead and solve for it. I have that the acceleration, I have the relationship between the acceleration and the angle of the ramp with the top equation. Oh, that's not going to work. Okay. With the top equation. So if I was given the angle of the ramp, I could plug that in here. I know g is 10 meters per second squared, so then I can solve for the acceleration. Or I could solve for the angle, and I'll go ahead and do this because I know some of us haven't taken math in a while. So if I wanted to solve for the angle using these equations, I would divide both sides by g. And so I would have ax over g is equal to the sine of theta. And then I would have to take the inverse sine of both sides. So the inverse sine is the inverse of sine. I guess that kind of seems a little bit redundant. But all that it really means is that if I have the sine of theta and I take the inverse sine of theta, these two functions, in a way, they cancel each other out. So then theta is defined to be the inverse sine of ax over g. So if I wanted to solve for theta, I would use this equation. If I wanted to solve for the acceleration of the block, I would use this equation. And then this is solving for the normal force of the block. Notice that when I had just a block on, a flat ground, and I looked at the forces, I'd find mg pointing downward, normal force pointing upward, and as long as there's nothing else acting on the block, then I would find that the normal force is equal to the full mass times the gravitational force. On the ramp, that's diminished a little bit, and the normal force, instead of being just mg, is mg multiplied by the cosine of theta. Okay, great. So this is a different scenario. Just wanted to see how it related. So we have equation for the normal force. We have the acceleration of the block. And we have the angle of the ramp that we could have solved for. We could have solved for any of these things given some kind of information about the problem. Notice that I kept everything really general. I didn't choose any particular value of the angle of the ramp. So that means that these three equations, let's go ahead and slide this work over here. Oh, no, sorry. These three equations are true for any problem that contains a block on a ramp where the only forces acting are gravity and the normal force. As long as the only forces acting are gravity and the normal force, these equations describe my block on the ramp system. So I suggest walking through it a few times just to make sure that you can reason why everything, you can reason through like why I made every step that I did. If you have any questions about anything that I did, feel free to ask, but walk through it yourself a few times, see if you can derive these equations. But once you've derived them and you feel comfortable with them, then you can just use them directly. If you see a block on a ramp problem, these are the equations that you're going to use. Again, as long as the only forces acting are the force of gravity and the normal force. Great. I'd love to hear any suggestions that you have. And if you have any questions, feel free to post them again to the discussion forum or send them to me in an email. And good luck.